We have been studying electricity. We talked about capacitors. We've talked about resistors and Ohm's law. We learned how to do combinations of resistors and capacitors. Today we're going to learn how to solve electric circuits that are more complicated. Now, do I have any students who've already taken electric circuit class? Okay, then there won't be that confusion because they learn a little more sophisticated method of doing this. And then when I go with the basic method, they're like, but. So here's an example of a more complicated circuit. In this circuit, we have, in the circuit, we have 1, 2, 3, 4, 5 resistors. 2 of those resistors are written with a lowercase r, this one and this one. That's because those are kind of a way of modeling a real battery versus an ideal battery. So we're going to start today by talking about how we model a real battery based on an ideal battery. And then if you look at the circuit, if you look at it carefully, you see that, like this resistor here, can you find any resistor that it's in parallel with or any resistor that it's in series with? Remember, if it's in series, there has to be no other option but the current that goes through one must go through the next. That's series. And for parallel, the tops of the resistors and the bottoms of the resistors have to be connected together. So R1, one side is connected to E, one side is connected to A. There's no other resistor that has one side connected to E and one to A, so there's nothing in parallel with it. There's no resistor that's in a straight line with it without any branching, so this resistor has no series or parallel. Which means that you can't combine it with others. So the methods we've learned as of Wednesday aren't going to suffice to solve this problem. It can't be solved with what we learned on Wednesday. We have to go further. So that's what we're going to do today, is learn how to solve more sophisticated problems. I'm also going to spend a fair amount of time showing you how to solve the problems on your calculator to make calculations simpler. Obviously, you don't have to do it the way I'm going to show you, but it will save you large amounts of time. So first, that lowercase r. Now, I don't know where I got these figures from. I think I got them from the textbook site. That is supposed to be a script E. So everywhere you see that funny E, that's what it's supposed to be. And it's short for EMF, which is electromotive force. So that E is the electromotive force, the EMF. It comes from a now proven incorrect theory about how batteries work. So the name is incorrect. It's an anachronistic term, but we still use it because, inertia of names. So what is the EMF, the electromotive force? If you just take the words, it would be a force to move charge. Electromotive force that moves charge. Because people thought of batteries as things that put a force on electrons. So electron comes in, there's a force put on it, and thus it moves. But then as they started learning what's going on with chemical reaction and whatnot, they said, well, no, it's not putting a force on the charge, it's something completely different. So that idea has been repudiated, but we still use the term EMF. And so the EMF now is an anachronistic term, like I said, that means terminal voltage of battery with no load. So I mean, I got to explain all of these terms or else you're like, I don't know, he said crazy things. Must mean something. A battery, if you draw a physical battery, it's got two terminals. The positive one, the cathode, and the negative one, the anode. The terminal voltage is the voltage difference between the cathode and the anode. Under no load means if you don't have any current flowing. If it's just there stationary, nothing is using it. So the EMF there is the maximum voltage you could ever get out of a battery. Now the batteries, because they are a chemical reaction, as you start using the battery, that terminal voltage is going to drop because the chemical reaction has to replenish it. You have maximum voltage, you have a little charge that leaves, the voltage drops, the chemical reaction kicks into gear to try to replenish it, but you're always going to drop down a little bit once you start to use it. And so that's where the resistance comes in. That lowercase r is called the internal resistance. And that's a number that, using Ohm's law, tells us how much the voltage drops as we use current. So if you have a nice, fresh, new battery, that internal resistance should be a pretty small amount. So you'll often see numbers like 0.5 ohms or 0.25 ohms, a small resistance, because you shouldn't have much voltage drop when you're using the battery if it's a nice, fresh, new battery. But if the battery's gotten older, you've got the chemical reaction has gone on, and you have, like if it's the lead acid battery, you now have sections of that lead plate that have been oxidized, or actually turns into lead sulfate on both plates. So you have more buildup of lead sulfate, which is going to make the reaction occur less efficiently because it needs to get to either the lead or the lead oxide. And so the internal resistance rises as the battery gets older. Now this leads us to one initial concept that we can understand. How do you test to see if a battery is good? What? You drop it. Okay, now the drop test, I actually don't know how well it works, and it would depend on the kind of battery you're using. But the theory is that if the chemical reaction is all fresh and new, it bounces differently than if it's done a lot of chemical reaction. I haven't paid attention to that one. I'm not saying it's wrong. Mind you, I just don't know how it's supposed to work. But that is a legitimate answer. Drop it. What's another way? Let's say it's a 9-volt battery. How do you check to see if that battery's good?
Lick it.
You lick it. Why do you lick it? That's nasty, man. You're licking a battery. How many mice have beat you to it? Why do you lick it? I think that is the answer I was looking for, by the way. Why do you do that? Yeah. Do you get a sizzle on your tongue or not? If you get good sizzle, it's a good battery, right? Well, what is that sizzle? What are you actually measuring with that sizzle on the tongue? The current. Why do you do it on your tongue and not on your, why don't you just stick it here on your forearm? It's not just more sensitive, it's wet. Because it's wet, the resistance is very small across the tongue, which means that 9 volts can make a significant current. Whereas if you did it on your dry skin, that resistance is really large and you can get nothing. Now you could say, oh, but I know better. I am going to slice myself open and stick it on the wound. Sure, I suppose that would work, but it's a little extreme. I hate to have a sizzle on my tongue, so I like to slice myself and test that way. Bad manners. So what you're looking for is you're measuring, in a very practical way, the current by how much sizzle you're getting on the tongue. The more current, the more sizzle. The more current it produces, the smaller that internal resistance, the better the battery is. Now, the answer that would have been wrong would be, I take my multimeter and I measure the voltage across the terminals. If there's no load across the terminals and you measure the voltage, what should it be? It should be that EMF, regardless if it's a good or bad battery. It's only when you put it under load that you're going to see if it's a good battery or not. So just measuring the terminal voltage is not really definitive. And different types of cells, right, different chemicals, will have slightly different terminal voltages. But it's the current you get when it's under load that's going to tell you, because that tells you, how much internal resistance you had. So anytime we see a real battery in a circuit, it's going to have this little lowercase r that's the internal resistance that's telling us about how the chemical reaction is working. Lower internal resistance, chemical reaction is working more efficiently. Okay, here is the same circuit that we started with. It has this resistor that's neither in series nor parallel with anything. Now, R2 and R1 are in series with E1, right? R2 and R3 are in series with each other and E2. So we could do things to simplify those, but we can't do anything with R1. So we have to have another method to solve this circuit. And that other method is using Gustav Kirchhoffs laws. Kirchhoff came up with two laws, and he's like the ultimate genius because he came up with two laws that are simple restatements of things that everyone should know. We have two clicker questions. The two clicker questions are about these two laws. So the first law, called Kirchhoff's current law, or the KCL, some people also call it the node law, says if you find a node, what's a node? A node is equal to a place where two or more circuit elements meet So if I have, like, looking at this previous picture, here I had resistor, internal resistance 2 and resistor 3 met right here. And so that is a node. That's a simple node. Nobody cares about simple nodes where you only had two things meeting. This here, we had three things meeting. We had R1, capital R1, lowercase r1, and R3. We call that an essential node. The essential nodes are the only ones that we're going to work with. So we'll be lazy sometimes and just say node and mean essential node. But with Kirchhoff's current law, it's called the node law because it works at any node. And Kirchhoff's current law says charge cannot be created or destroyed. Now you're like, really? That's Kirchhoff's current law? I've never seen it written that way. No, not written that way, but that's what it means. Kirchhoff's current law says that in our circuit, we don't have anything that stores or produces charge. We have things like batteries that give energy to charge, things like resistors that take energy away from charge, things like capacitors that store a separation of charge, but they don't store charge. It's a separation of charge. The net charge on a capacitor in a circuit should be zero. So we don't have things that store or supply or absorb charge in our circuit. Hence, any charge that comes into the node must leave the node. Since current is the flow of charge, that statement that any charge that enters must leave is equivalent to saying any current that enters the node must leave. And so Kirchhoff's current law can be written in either of two ways here. The sum of the currents at a node is equal to 0, or the sum of the currents into the node is equal to the sum of the currents out of the node. So sum of the currents at the node means that if it's coming in, let's call it positive. If it's going out, it's negative. The sum of all of those currents has to be 0. So they mean the same thing. You can use it either way. No one is ever going to call you and say, no, you can't use sum of the currents equals 0. You have to use currents in equals currents out. They mean the same thing in the end. So if I look at this little circuit segment, I have current I1 is coming in, and I have currents I2 and I3 are going out. And so Kirchhoff's current law says either IN is 11 amps equals I out, which would be 7 amps plus 4 amps. So that's using this method. Or I could have said the sum of the currents, I'm going to say coming in is positive, so I'd have 11 amps in minus 7 amps out minus 4 amps out equals 0. Those are two applications of the current law on the same node. They're both true statements. We can all look at that and say, yep, 11 minus 7 minus 4 is 0. And yep, 11 equals 7 plus 4. So that's Kirchhoff's current law. You do need to know this, and you're going to use it, probably, let's say, 3 of the 5 problems for the homework that's due on Monday, at least. So, any questions about Kirchhoff's current law? Now, I'm going to come back and talk about utilization later, but right now, we just want to make sure we understand what it is. So, first clicker question. What law is Kirchhoff's current law a restatement of? Uh-oh. Waiting on one. Okay. I did not memorize it. Oh, Ashley, great. You answered the next one. Oh, hey, I actually was able to get back and see your answers. That's startling. So here's the answer breakdown. We had some changes to the correct. So now that we have a clear majority on conservation of charge. Kirchhoff's current law is simply restating conservation of charge as applies to an electric circuit. So it's a very fundamental law being applied. Now, Kirchhoff's voltage law, also known as the loop law. And the loop law is, again, a very simple statement. It's a statement about conservation of energy. So the node law was conservation of charge. The loop law is conservation of energy. What the loop law says is if you start at some location and you go up and down and all around and you get back to your starting point, you're going to be at the same energy. That is, you go as an electron goes through the circuit, it may gain some energy some places, it may lose some energy some places. But when it gets back to the starting point, it's going to be back to where it started. It's kind of like saying if you go hiking, if you start at the entrance to Union College and you hike all around, remember Peanut Hill is the tallest hill in the city of Lincoln, and you end up back at the entrance to Union College, you're going to have the same potential energy as you started with. Why? Potential energy is mgh, right? You're at the same elevation, same potential energy. In a circuit, it's the same thing. You start somewhere circuit, you go all the way around and get back to where you started. It doesn't matter what path you take, you're going to be back to the same potential energy, which means same potential energy per charge. And what do we call potential energy per charge? Potential energy per charge is the focus of the week, voltage. So you go all the way around a circuit and you're going to end at the same voltage you started with, which can be written mathematically as the sum of the voltage changes as you go through a loop is equal to 0, or the sum of the voltage rises is equal to the sum of the voltage drops. So just like with the Kirchhoff's current law, there's two ways you commonly see it. Now this picture, I just need to explain this picture. This picture is showing the circuit as a flat circuit. So that's the circuit that I did in red. And then it's showing on the vertical axis the voltage, because voltage is analogous to elevation, right? Potential energy of the charge is the charge times the voltage. Potential energy of a mass is the mass times the elevation times g, of course. And so the vertical is showing you how the voltage changes as you go around the circuit, and you get back to the same starting voltage. Now, if we look at this circuit, the circuit itself is a little more complicated. Number one is I have to choose a starting point. So my default is I always start at the bottom left corner of a loop. Why do I do that? Simply so I know where I started and where to end. You could start anywhere, doesn't matter. Just make sure you remember where you start and where you end. And then I have to do a loop. I can choose the direction of my loop, either direction. I can go clockwise or counterclockwise. By default, I always go clockwise. So I go around the loop like this. Next thing I need to do is to determine the voltage rise or drop for each element. So this has the current shown. It says it's 2 amps. So if that's 2 amps, the current goes like this. Let's change to the same color as the current. I always, and when I say I always, I'm saying these are really good practices for you to do. You don't have to. I always draw an arrow showing the direction the current goes through each resistor. The reason I do that is because I know that a resistor is going to take away energy. That is, it's going to lower the voltage. So if the current comes in here and goes out here, it has to have lost energy, lost voltage. So the side where it goes out is going to be the negative side. The side where it came in is the positive side. So for each one, I indicate which side is positive and which side is negative. The negative is on the side where the current exits, where my arrowhead is. The positive is on the side where the current entered, where my tail of the arrow is. Now, a question you might ask is, what if I'm wrong on my current direction? It'll be okay. It'll be okay. You will many times, like in lab next Tuesday, I think it's next Tuesday, you will have to guess on the direction of the current. You won't know beforehand what direction it's going. So you'll just guess on the direction of the current. You'll draw your arrow for that current. You'll identify which side's positive and negative. You'll go through and do your calculations. And you might find that, oh, the current's negative. Well, that just means your arrow was the wrong direction. All the numbers will still be right. Okay, now that I've identified the direction of the current, for each of these, I go through and say the voltage is equal to IR. So I use Ohm's law to find the voltage drop across each resistor. Now that I've done that, I'm able to make an equation for the loop that says the sum of the voltage rises equals 0. Sum of the voltage I said rises, I didn't write down. And so I just start here, going from here to here, according to my picture. Going from plus to minus is a drop. So I have minus IR2. Then I go from here to here. I know the numbers are written on the circuit, but how do you know which side's positive for that power supply? The longer one is the positive. So for that power supply, this side is positive, this side's negative, so that's a rise. Then I have my next resistor going from plus to minus is negative. My next resistor going again from plus to minus is negative. And that gives me my equation for the loop. So there's the Kirchhoffs Law equation for that loop. So we have two kinds of equations we can make for a circuit. One's using Kirchhoffs voltage law, one's using Kirchhoffs current law. And then for solving a circuit, we're going to use those together to solve the circuit. So let's get to our second clicker question. And then, okay, I got to hit redo because Ashley popped an answer in when it was goofing up. What law is Kirchhoffs voltage law a restatement of? Press harder. Gonna have to do the Irving walk. There it goes. Okay, this time we all answered correctly. Kirchhoffs voltage law is a restatement of conservation of energy. Can't create or destroy energy. It's conserved. This here is showing the sign conventions I just went over. The direction you go through is important for the signs. You have to pay attention. So here's a circuit for us. Now it doesn't have any numbers for the currents or the voltages except for the power supply. So this is a full-on circuit for us to analyze. Now, once again, it has a resistor that's neither series nor parallel. We can't simplify it and solve it that way. We have to use Kirchhoffs laws. So there's a couple more rules that I haven't stated. I've only given you the tools. Here's the rules. First, identify all essential nodes. How many essential nodes do I have? Just blurt it out. 2. How many nodes are there here? Each node is marked, right? A, B, C, D, E, F, G, H. Those are all nodes. Well, let's be a little more careful. D, E, and F are all the same node, and A and H are the same node. But A, B, C, E, G, those are all nodes. A, B, C, E, G. So there's 5 total nodes. But 3 of those are non-essential. What makes a node essential? More than 2 elements. There's only 2 places where we have more than 2 elements, here and here. We're only going to apply Kirchhoffs current law to one less. So all but one of the essential nodes. Of course, that brings up a really good question. Why would you use all but one of them? Why not use all of them? I'll give you the answer. You don't use all of them because the last one would be redundant. The last one would just be the combination of the others. And so we need unique equations to solve, not just equations. We can't just say, well, A plus B is equal to C, and 2A plus 2B is equal to 2C. Those are the same equation fundamentally. And that's what you would get if you used the last one. So for this circuit, doing step 1, I identified all of the essential nodes. For step 2, I'm going to apply Kirchhoffs current law to all but one of the nodes. So I am going to just start in the back. Alex, choose one of the 2 essential nodes. A. So we are going to apply Kirchhoff's current law at node A because that's what Alex chose. Sum of the currents at node A equals 0. So if we look at node A, what currents do we have coming in? Still with Alex.
We have one coming in from the right.
Well, they have names. By the way, notice all of the currents are named. I should have put that in there. I should have said name all the currents because you need to. And notice that I2 is going through from one essential node to the next essential node. It's the same current because these are in series. There's no other alternate pathways. So coming into node A, what's coming in? I1, I2, I3. Okay, so I1 is positive. What's going out? I2 and I3. So those are going to be negative. So my sum of the currents equals 0. Now, just for grins, what if Alex had chosen node E? How would that have changed things? If I do the sum of the currents at node E, what's coming in is I2 and I3. And what's going out is I1. What's the difference in those two equations? The minus sign. Equation 1 is minus equation 2. So they're the same information. That's why we can't use both. So I'm just going to not use this one. I'll cross it out because it's identical to the one above. Okay, so we've applied Kirchhoff's current law to all but one. Next, identify each mesh. And now you're like, what? You haven't said the word mesh today. Well, a mesh is a crazy word in circuits only to mean smallest loops you can make. You could make a total of 3 loops here, but how many smallest loops can you make? 2. The meshes need to cover the entire circuit with the smallest loops you can make. So basically you take a circuit and you just take each small loop you can make and name them. So I'm going to call this mesh 1 and this mesh 2. So you identify each mesh and then, see, any color black it is. Then you apply Kirchhoff's voltage law to each mesh. So we go to step 4. There's 2 meshes, so James, I will give you the first mesh. So we look at the first mesh. We're going to apply Kirchhoff's voltage law to it. So you have to first choose a starting point, so where you want to start. Okay, so he's going to start at node A. And what direction are you going to go about? Clockwise or counterclockwise are your options.
Yeah. I'm vague because you said you go clockwise, but the current's going counterclockwise.
Well, in mesh 1, it's going clockwise, but
Yeah, clockwise.
okay, so he's going to go clockwise. So now we're going to do this. The sum of the voltages on my mesh 1 equals 0. So now I fill it in. So I start at A and I go through this resistor. So the current is going up. Which side is positive on this resistor, the top or the bottom? I'll draw a picture over here just so we're clear. The side with the tail of the arrow is positive. The side with the arrow head where it's coming out is negative. So the bottom is the positive, the top is the negative. So that's a voltage drop. So I'm going to have minus, and I'm not going to write 2.5 ohms because it takes more writing than R2. So I'm just going to put Ohm's law, I2, R2. Now I'm going to have you say the rest of them, okay? Now we go through the circuit. We've gone through that resistor. The next thing we get through is EMF number 1. Is that going to be a voltage rise or a voltage drop? So should I use a plus sign or a minus sign? Good call. Keep going. I get to this resistor. Which side is positive for R1, left or right? Okay. So is that a voltage rise or drop? Okay. So I use minus. And what do I put now? R1 times?
Oh, R1 times I1.
That's actually I2.
Oh, okay.
Keeping track of these is obviously important. Okay, we keep going through the circuit. What's the next thing we come to on mesh 1? Okay, we come to the junction. We just keep going.
Oh, okay. Then you go to your next resistor.
Which is?
And this one would be big R1.
Yes. And which side's positive here?
The right side.
So that is going to be plus or minus in my equation?
Minus.
Minus. And
That's R1 times I2. Big R1.
it's big R1.
Oh, which is I1 then.
Right. You have to pay attention to which current it is, right? Makes the difference. Now we're back to where we started, so equals 0. So there's our second equation. Now that's clearly different from the first equation we found. And now, Brandon, we'll go to the next. So you have some of the voltages on mesh 2. Yes, ma'am. Because that was a voltage change on the circuit. I was doing the sum of the voltages on the circuit. And so when I go through the battery, the voltage rises, in this case, by 18 volts. So that's why I put it there. Right? It's not just looking at resistors. It's everything in the circuit. Okay, so Brandon, where do you want to start? Okay, so he's going to start at A again. And do you want to go clockwise or counterclockwise? Okay, so he's going to go counterclockwise. I'm actually going to change the direction I drew for my mesh so it matches the direction that we're going. Okay, so starting at A, going counterclockwise, the first thing we come to is, okay, what is the first thing we come to? I can't hear you. Okay, and there's going to be a positive or a negative? It's positive because we're going from the negative side to the positive side. Okay, what's the next thing we come to? Okay, and are we going to have a voltage rise or drop? Okay, we have currents like that. So this is a positive, this is a negative. He's right, it's a drop. So minus, and then what do I have minus? All right, what's my equation for the voltage drop? Okay, next thing we come to? Big R3, and is that going to be a voltage rise or drop? It's going to be a drop as well for the same reason as before. So minus, and what do we have for the voltage? Okay, and then we keep going. What's our last thing? Okay, is that a rise or a drop? And its equation will be? Now we're back to where we started, so that's equal to 0. So we have 3 equations. I'll put these 3 equations in red boxes so we don't lose track of them. Yes. For the E2?
For the mesh 2, I1 multiplied by the big R1.
You're talking about.
Never mind.
Okay, but I'm pretty sure everything's correct here. But I was trying to figure out where you're talking to make sure. So we have 3 equations. How many unknowns are in these equations? Let me start by saying all of the resistor values were given. I just used R because it was easier to write. Also, all of the battery values were given. I just used the E, script E, because it's easier to write. So how many unknowns do I have? How many variables that I don't know the value for in this circuit? 3. What are their names? I1, I2, and I3. So I have 3 unknowns. By math theory, if I have linear independent equations, I need the same number of linear independent equations as unknowns to solve it. So if I have 3 unknowns, I need to have 3 linear independent equations. I do. So that means by math theory, I can solve these equations and find what each of the currents are. And then once I find those currents, I can use them to find the voltages across each resistor. So I can completely solve the circuit with these equations. How? My son in his math classes has to do things like, well, let's combine these 2 equations to eliminate this variable, and then combine that with another equation to eliminate another variable. And with 3 equations, it's doable. When you get to 7 or 8, it's really, really untractable. And that's why we use linear algebra. So our equation, I can summarize these equations, and I will show you how we do it here. The first equation I'll make no change to. Just leave it as it is. The second equation I'm going to rewrite as I1 is multiplied by minus R1 plus I2 multiplied by, and that was minus R2 minus lowercase r1 plus I3 wasn't that equation, so multiplied by 0. Let me make it smaller. Equals minus E1. So I moved the constant to the other side of the equation. Now you might notice I have minus signs everywhere, so it's convenient to make everything positive. And so that's rewriting that equation. And likewise, for the next equation, I could have rewritten it as I1 times minus R1 plus I2 times 0 plus I3 times once again changing all the signs. So those are equivalent equations. What have I done? I've now written it I1 times a constant plus I2 times a constant plus I3 times a constant equals a constant. So I've written my equations in a different form. And that's what I have here. This is those equations rewritten. So I have I1s, I2s, this one's not going to form a nice, and I3s, forming columns, so to speak, and then I have the answers. And at this point, I haven't established how this is going to help us at all, right? Well, the first thing we do is recognize that we can write that set of 3 equations as a matrix where I took the thing that I1 was multiplied by and put it here. The thing that I2 was multiplied by and put it here. The thing that I3 was multiplied by and put it here. Then I have a column vector I1, I2, I3. When you multiply matrices, you take, for the first row, the first item times the first item in the column, plus the second item in the first row times the second item in the column, plus the third item. So if I read the top, I have I1 or R1 times I1 plus R2 parentheses R2 plus lowercase r1 and parentheses I2 plus 0 I3 equals, and then that position in the answer is epsilon 1. This matrix is just rewriting the same equations. So how you do it is you take your equations and you just put the coefficients for each of the i's in the matching place in your matrix. And now a little linear algebra that You don't need to know, but if you're curious, what we have is the form, this matrix multiplied by this column vector is equal to this column vector. And using linear algebra, if I can find the inverse matrix for A, and I put it on both sides, inverse matrix times the matrix gives me the unit matrix, so I just have the current column vector is equal to that inverse matrix multiplied by E. So if I find the inverse matrix and multiply it by E, I'm good to go. Well, your calculator has a built-in function to do that. If your calculator is, a higher level calculator. That function is called row reduction echelon form. And so what we're going to do is take what we have here and put it into a matrix and find what the result is. So I don't remember the values. R1 is 2. What is R1 is 6, R2 is 2.5, R3 is 1.5. Nice. So using those resistors, we were able to replace R1 is 6 ohms, R2 plus R1 is 2.5 plus 0.5 is 3, epsilon 1 or EMF 1 is 18, and then the next one, R1 is 6 again, 0, R3 plus R2 is 1.5 plus 1/2 is 2, 1 minus 1 minus 1. We have everything in matrices. Now on your calculator, you need to create, because this is 3 this way, 3 this way, and 1 here, we create 3 rows by 4 columns matrix. So we took this matrix here and slammed it together with this here to make this 3 by 4. And now, depending on the type of calculator, I actually have the instructions, what type calculator. I have it for the TI-84. If you have a Texas Instruments, it's going to go something like this. If it's something else, the fact is I'm not sure how to do it. We'll have to figure it out. If you want to come, I can try to help you. But you make a matrix. So on TI, use the second function matrix, go to edit, choose a name. So like choose the name A, for instance, and then make it a 3 by 4. Now, I want to go slow enough that people actually can follow along because, like I said, this saves you incredible amounts of time. When we do lab on Tuesday, I'll have a spreadsheet that does this for you so you don't have to use your calculator. But it's important to do. So, is anybody still trying to make the matrix? Okay, I'm going to assume everyone that's following along has done it. So now after entering the matrix, so now we need to enter or edit the matrix. So you put in all the numbers. Got to put in all those numbers. I have 1 minute. I guess I won't wait. I thought I had more time. Then you go to your matrix math. Choose row reduction echelon form, which is near the bottom. It's quickest to get there to use the up arrow to get to it. And so you do second matrix math, go up to the row reduction echelon form and hit enter. And then you do, again, the second time, second matrix name and choose your name and hit enter again. So I missed putting an enter in right there. And then it's going to give you a result that looks like this. It gives you another 3 by 4 matrix. The first 3 are just the unit vectors. And the way you read this is 1 times I1 is this. So this here is I1. 1 times I2 is this, so this here is I2. And 1 times I3 is this. That's I3. So you have your currents pop out of your calculator just like